Hi, my name is Yipkei Kwok. The title of my presentation is Assessing the Improvement Space and Performance Tuning of Learning from OPT, a state-of-the-art artificial intelligence-based caching scheme for content delivery network. This is the overview of this presentation. First of all, there is going to be a slide about myself, and then I will give some background about content delivery network and caching schemes. And then we are going to talk about a caching scheme on which we're developing a variant. And then we will have a conclusion and future work. And at the end, it's going to be an acknowledgement. So about me, I am an assistant professor in computer science. So in the Department of Computer Science, Mathematics, and Physics under College of Science and Health at Missouri Western State University. So background about content delivery network. First of all, what it does. The goal that a content delivery network is trying to achieve is to provide low latency access to web objects. So low latency, every time when we request an object, say like a YouTube video, it takes time for the video to show up on our screen. So between the time it takes for us to request a video until we obtain the video, that amount of time we got a latency. So without traditionally, when there's no content delivery network, what happens is that regardless where you are, if you want a certain video, the request is sent all the way to the content provider, which is very likely somewhere far away from you. And then the content provider respond with the requested web object. Now, so the farther the user is from the content provider, the longer time it takes for this. For the transfer of the object. So then the longer the latency. The content delivery network is a solution to this latency problem. So it is a network of geographically distributed cache server. So those cache servers are distributed across the continental, and so these server cache are commonly accessed web objects. So when a user requests a certain web object, say a video, the actual request is sent to the to a cache server that is nearby. And then if the object, if the server has this object, then the object is going to be sent to the user directly. And because the server is nearby, the latency it takes to obtain the object is really short. Now let's say in this case the cache server does not have the object. So what the server does is that it forwards the request to the content provider, and then the content provider responds with the request object, and then the server forward the object back to the to the user. Okay. And when the server receives the object from the content provider, the server may cache the objects so that in the future, if the object is being accessed again, then the server can just serve the object rather than forwarding the request to the content provider. the effectiveness of a content delivery network depends on how mm, um, how how many requests it can um, it can fulfill without forwarding the requests to the content provider. Uh, the the okay, yeah, the proposed metric for this measurement is called object hit ratio. Let's say if the object hit ratio is 30%, for every 100 requests, um, only 30% of them can be fulfilled on the server. The other 70% will have to be forwarded to the content provider. The lower the lower the object hit ratio is, the more requests have to be forwarded, and the less effective the content delivery network is. Now, a major factor of the object hit ratio is the um, caching scheme. Now, let's take a look at the I mean, yeah, at, let's take a look on what happened when the request arrive is in a server. If the request object is in the server, then the server um, send the object to the user. In this case, we got a hit. But if the object is not in the server, then um, the once the server receives the object from the content provider, the server has to decide if it is going to admit the object into the cache or not. If the decision is to not admit the object, then the server will just send the object to the user. But if it decides to admit the object, and if this enough space in the cache to store then the new object, then in that case the server will just admit the object and then send the object to the user. However, if the server is full, then um, the caching scheme decide which object to evict and then to admit object, and then it evicts enough object to make room to admit the new object, and then it send the object to the user. Now, the caching scheme decide which object to admit and which object to evict. This is what a caching scheme does. So how does a caching scheme make the decision? Often it is based on heuristics. For example, usually, say if I have a few objects in the cache, object 0 and object 1, the less frequently an object is accessed, the less likely that it is going to be accessed soon. So then it may be a good candidate for eviction. Likewise, if I have a few objects in the cache, the one that has just been accessed is usually being accessed soon in the future. Okay, so if I want to, in this case, okay, I have two objects in the cache, 0 and 1, and object 1 has just been accessed. And in case if I want to evict an object, in this case, I will want to evict object 0 because object 0 has not been accessed longer than how long object 1 has been accessed. It depending on the caching scheme, if least frequently used is used, in this case, we will want to evict object 1 because object 0 has been accessed 3 times while object 1 has been accessed for only once. And the problem is that the heuristics do not always hold. Say, for example, the most recently accessed object may never be accessed again. In this case, we would not want to keep it into the cache. And when heuristics do not hold, the performance becomes bad, which means that the effectiveness of the cache server degrades. Now the solution is that rather than using heuristic, we can make a cache decision based on the actual object access behaviors. And there are multiple solutions out there. Our focus is on AI-based approach. Here is a recent AI-based caching scheme called LFO. It was proposed by a postdoc in Carnegie Mellon University. It uses AI to predict optimal solutions. To predict optimal solution means a decision on caching the caching decision, which is to whether to cache the object or not. So the related questions are how do we determine the optimal decision? How do we know how do we know if a decision is optimal? Second, just like human, when we make decisions, we're based on some input in order to make decisions. For AI, we also need to give it some input so that the machine may make that decision. So, what are the input? The third question is that what if the behavior of the object changes? Okay, so the way we deduce optimal solution is that there are lots of requests. We divide the request into windows, where each window has a certain number of requests. And then we use a technique called practical flow-based offline optimal, in short, PFO, to deduce the optimal decision given a certain trace sequence. Okay, here is a request sequence in a window, and then we provide the request sequence into a PFO, and PFO tells us the optimal decision that will lead to the highest object hit ratio. Now the question is, this request sequence is something in the past. Okay, those are the requests that are in the past, and these are the decisions that are suggested for requests in the past. But these requests are gone; they're not going to come again. So, which means that it is too late to execute these decisions. So, how can we use what happened in the past to tell us what to do in the future? The way to do so is that at the end of each window, we extract some features from the request sequence, and then we also obtain the optimal caching decision again through PFO. Now, so what are the features? Features are object access behavior, the actual object access behaviors, and the object properties. These object access behavior may include the time intervals between recent accesses, object size, and some other items. So now, given the request and in the window, we obtain the features, and then we use PFO to obtain the optimal decision on whether to cache or not cache the object requested by each request. And then, so we input the features and the decision into the AI model. Okay. So it is basically just like this. We are telling the AI model, okay, under this feature, which means that under this scenario, under these conditions, these are the caching decisions that you should make. This is how we teach the AI model, so that in the future, when the AI model encounters similar features, it it knows if it should it cache the object or not. Okay, so the third, so now when we have the model that an AI model that has been trained. So um, how can we use this model to help us to make a decision in the future? So this is how in uh, after training we begin a new window, and these are requests that are coming. Okay, uh, these are not requests in the past. These are the requests in the present. In the present, when request comes, we extract the we know the object requested by each request, and then we obtain the features of each of the object and enter the features into the AI model and let the AI model tell us if we should tell us if we should capture the object or not. The way I mean, the output of the AI model is actually the likelihood of if the request object will be accessed in the future. The bigger the number is, the more likely that the object is going to be accessed in the future. Now, so the author of LFO drew the line at 0.5. If the likelihood is at least 0.5, then catch the object. Otherwise, do not catch the object. We are developing a variant of LFO. Our efforts are twofold. First, so far there's no published data to show the distance the performance gap between LFO and PFOO, which produces the theoretical maximum object hit ratio. So we are going to assess the improvement gap. The wider the gap is, the more room we have for improvement. The implementation of PFOO is publicly available. However, there are two problems. One, the execution time is prohibitively long. Two, it consumes a lot of memory that conventional computers cannot run. To overcome this problem, we propose these solutions. First, we are going to make the execution of PFOO parallel. So which means that multiple parts in a program can execute at the same time, running on different processors. Then in that case, uh, we can run PFOO on a multi-CPU machine. Second, memory intensity. Our proposed solution currently, what happens is that um, PFOO load the entire request file. This is a request trace. A request trace basically is a record of each record or of each request. So currently, FO load the entire trace into the memory before processing, and it takes up a lot of memory space. And what we are what we propose to do is to change the program, the implementation of PFOO, so that it takes request trunk by trunk and operate one trunk at a time in the memory to conserve some memory. Okay, so uh, another uh, another another place that we propose to improve about LFO is that uh, we we believe that there are scenarios when LFO actually evades object that it is not supposed to. Say, for example, um, in this case, okay, this is a new object, and because the likelihood is at least 0.5, so LFO would emit this object. And then now the cache is full. There's no room for this new object. Um, the, there's no room. Okay, so LFO is going to evict objects that are the least likely to be evicted. In this case, it is these two. However, if you look at this object, its likelihood is 0.6. It is even more likely to be accessed than the objects are about to be emitted. So our proposed solution is that before emitting an object, examine the likelihood of um, objects that are potentially to be evicted. And if any of them have likelihood that are bigger than than the object being emitted, do not emit the object. This is our proposed solution. So, future work. This work laid the groundwork for performance optimization for some other AI-based caching scheme. We want to see how much we can learn by optimizing LFO and apply the lesson on some other AI-based caching schemes. In the future, we also want to see what other AI-based techniques such as neural network that can be used for caching schemes. We want to acknowledge Missouri Western State University, the Portal program, as well as the grant incentive program for their support on this work. Thank you.